Hi, this is Steve Rostedt, and today I'll be talking about using Libtracecmd to analyze latency and performance troubles of your application. A little about myself. I'm one of the original authors of the PreemptRT patch set. I'm the creator and maintainer of ftrace, which is the official tracer of the Linux kernel. I also created make local mod config to make your builds much quicker. And I'm the creator and maintainer of KTestPL, which is a tracing infrastructure inside the kernel. But since I don't have much time, I'm going to get right to the talk. And that is tracing kernel latency of your application. Why? Because the kernel is a black box, and your application is at the whims of the kernel scheduler. So when the kernel says you're going to be scheduled in or out, it's up to the kernel that lets your application run or not. Interrupts can cause delays to your application. If you have a bunch of interrupts coming in from external devices, that could be a problem. And there's also a lot of locking within the kernel, and the kernel contention among those, or the contention among those kernel locks can add latency to your system. So all that could be seen by the tracing infrastructure to find out what's going on. It can monitor the scheduling decisions that the kernel is making, so you can see when the kernel is having or is causing the issues and your application isn't being scheduled on time and why. You can record the interrupts that are happening and for how long, and see how long kernel locks are held. So in this talk, I'm going to talk about a utility called Cyclic test. It's a way to test latency of your system. And the way it works is it calls nanosleep, which is a way to tell the application to go to sleep and then wake up at a certain time. And it will record when it expects to be woken up, and then when it is actually woken up, it will take the timestamp again and subtract when it was expected to wake up from, or where the time it actually did wake up, and that will tell you the latency or the jitter of the wake up time. And the real-time Linux kernel developers use this utility all the time to figure out how well the real-time Linux kernel works. What they'll do is they'll run it under load to see how the load affects the latencies. It will also, they'll run it for weeks, if not months or years. A single kernel just boot it up and run cyclic tests with its load, and then for a long time to make sure that the latency never goes above a certain threshold. And that's to weed out any issues within the Linux real-time kernel. Today, I'm going to use cyclic tests for this talk, but when we talk about could be used for any type of application. So here's a typical run of cyclic tests. Here's the parameters I usually use. The P80 is to say, hey, run all the threads at the priority of 80, which is a higher priority. And the I250 is to wake up at intervals of 250 microseconds. So every 250 microseconds, it will expect to wake up. -A says, okay, try to pin the threads at the CPUs they're number for it. So thread 1 will be on CPU 1, thread 2 will be CPU 2, so thread 3 will be CPU 3. -T says create as many threads as there are CPUs. -M tells cyclic test to mlock all of its memory, which is a way to lock the memory into, like, pull it in so that it doesn't take page faults, because a lot of times memory is done just in time and pulls things in later. And -D0 is a way to tell cyclic test to run all the threads basically in lockstep. By default, it will actually shift them, stagger them, so one thread will go off, and another thread will go off, another thread will go off, but in our example, we want all threads to go off at the same time. This is usually the parameters I use to test the real-time kernel anyway. So, cyclic test and tracing. So when a threshold does go, there is a threshold bigger than what we want it to be, we want cyclic test to stop and stop tracing as well, so that we could actually analyze what happened and why did it break that threshold. Even more so, we want cyclic test to write into the buffer when this happens so we can see what CPU it happened on. And this is the parameters I usually use for cyclic test to achieve this. -B usec, which is the break trace, is a way to tell cyclic test, here's the threshold I want you to stop at. And trace mark is a way to tell cyclic test to write into the Linux kernel tracing buffers when it happens. And here you'll see how I do that with adding the -B100. So if the threshold is ever greater than 100, it will stop, and the trace mark means it will write into the Linux kernel. Break value here was 561 over 100. And I'm going to use trace-cmd to see the kernel output. Trace-cmd is a utility. It's available in Fedora, Debian, SUSE, Ubuntu, whatever. You could download that. It will interact with the Linux kernel tracing infrastructure. So here, trace-cmd show will read what's in the Linux kernel trace buffers, and you'll see that the cyclic test wrote hit latency threshold 561 greater than 100. And that's our latency. Now, we can also use trace command to enable events that we want to trace to analyze. So when something does happen where our latencies exceeds the threshold, we'll be able to stop and analyze a bunch of events. In this case, I want to see the sched switch event, which is when a task is scheduled off the CPU and another task is scheduled on the CPU. The sched waking event is when a task went to sleep and an event came in and said, hey, wake up this event and get it to run on the CPU. And I'm going to trace all the timer events as nanosleep, or as nanosleep uses timers, and there's a lot of timer infrastructure that goes on to get that to work. I want all the events. I'm not going to be choosy about it, I'll just pick all of them. And I'm going to look at interrupts and interrupt vectors as well. So when interrupts come in from other devices, I'll be able to see that. Same here. So I ran this, I hit threshold 121 break value, and when I do trace command show, which is showing you what's on the inside the kernel buffer like I did before, you'll see there's a lot more information that has all the data there that I enabled. And because I want to run libtrace on this, so I have a tool that could analyze this data, I don't want to use the Linux kernel tracing buffer, especially if I reboot the machine, I lose all that data. I want to pull that out and extract it into a file. So I use trace-cmd export, which will read the kernel data and put it into a file. And then I can use report to see what's in that file. And here, the -L there will create that second column, which has a kind of cryptic. 6 is the CPU that ran on. The D is that interrupts were disabled. The dot, or capital N, means that need resched was set, which means that something woke up and wants to run, but a schedule needs to be done, and that's so need resched means we should call schedule. H is the interrupt context, or it means that we're in hard interrupt context, and 1 is and 1 in the 3 of those other numbers that preemption has been disabled. And down at the bottom, you'll see where it wrote into that. But importantly, we see it happen on CPU 1. So now we could run trace command report with --CPU 1. So we get rid of all the other CPUs and we filter only on CPU 1. And then we could follow what's going on just for that CPU to see why the latency happened. And there's CPU 1. And from here, I'm going to see where the cyclic test was scheduled onto the CPU. When it woke up, from here, this is important. This is the timer events, and that 8180 blah 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 on both expires, and then now these are the 2 timer events. So when cyclic test called nanosleep and said, "Hey, I want to wake up at a certain time," the internal high resolution timer code will say, "Okay." It will look at its internal timer and say, "Hey, here's when we want to expire at." Then when it expires, the event is actually going to show you the timestamp that it said, "Here's when it actually did happen," but it uses a different timestamp numbering offset, but they're both nanoseconds. That is, that this is done in nanoseconds, and actually the trace event timestamps are also nanoseconds. I'm going to use this information to convert it so I could synchronize the 2 together. Now, using libtrace to read the file, because we want to automate this process. So we're going to start from the end of the trace and work our way back. This way we can find the trace marker to find out where the problem happened, and then we could continue backwards to find other events. And then when we get to the very beginning of where the time was enabled, we're going to go forward to collect even more information. So I hope you guys know C, but if not, you can still understand all this. This is the libtrace API. It's pretty simple. So first thing I do is I'm going to create a handle to open the trace.dat file. So here the trace cycle.dat file is what I opened. And then here I'm going to call init data. I don't have enough time in this talk to explain everything I'm going to be recording. All this code is available. I'm going to have a link to it at the end of the talk, so you can look at this. And if you have any problems, my email is also available. You can feel free to contact me about how I use this tool. And now I'm going to call trace command iterate events reverse. This means I'm going to go to the very end of the trace.dat file and work my way backwards to find the trace marker. So here's the function I'm going to call that gets called at every single event, called find trace marker. Now, you'll notice that there's a marker equals d.marker, and that d is the data that I initialized that I didn't have time to talk about, and part of that initialization code was to map all the trace event identifiers in so I could look it up while I'm going backwards, because when I walk backwards and I look at the event, I'm going to extract the ID, which is that data type of the event. If this event doesn't match the trace marker, I don't care about it. So I return 0, which means continue and walk backwards. So once I get past this point here, I'm on the trace marker. So I'm going to extract that string that we printed out, and I'm going to use scanf to extract out the latency and the threshold from there. I don't really use this for this application. I just kind of showed you that this is possible. But what I do care about is the CPU that it happened on. So I'm going to take the record is the event representative, the raw data event, and I'm going to say, give me the CPU and record that in my data file so I know which CPU this all happened on. Now, back in my main file, or in my main function, I'm going to create a CPU mask so I could filter out all the CPUs and only use the CPU that I care about, which is the data.cpu. That's the D CPU field that I had earlier in the last slide. Now I'm going to continue my reversal. Remember, when I exit out with the -1, if I go back real quick, you'll see there's a return 1. That means stop the iterator right here. So now when I go here, I'll continue where I left off. I'm going to look for the scheduled switch event. Now here, I'm going to do the same thing where I'm going to ignore all the events but the scheduled switch event. And I want to record the timestamp of when the task was actually scheduled on. So this is when the cyclic test was scheduled onto the CPU. I'm going to continue to go backwards and look for when it was woken up. Same function, same thing, ignore everything except for the waking event, and then record the time that it was actually woken up. Now, I'm going to continue to go backwards, and I'm going to look for when the timer actually went off. And here, a little bit more information because I needed to pull out that the value, that 818 blah, 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 internal value of the high resolution timers. And like I said, that's in nanoseconds. So are the timestamps of the events in nanoseconds. So what I could do is, since the event that went off and the now that's went off, they're very, very close, I could say, okay, give me the value that pulled in, subtract it from the timestamp of the event, and now I have a delta that I could actually convert the timestamps of the internal structure of the high resolution timers to match the timestamps of the events. That way I could, compare apples to apples. And I'm going to continue to go back, and this is why that delta was important, because here's this is the event, the timer start of when the event was, when the timer was started. When the cyclic test called nanosleep, it said, okay, I want to sleep, here, call this, and again, I'm going to use that timer delta to convert the timestamp that I pulled out, which is the expects value. Remember, in that event, you saw, here's when we expect to expire. This is when the timer is going to go off, where we want it to go off, because that's the 250 nanoseconds here. We're going to take that internal timer and we're going to convert it to the times to match the values of the timestamps of the events. And now we could compare to see, like, okay, where did this have a problem? And look at that. So finally, here's the print of all that data. I'm printing out all the times when everything expired. I'm doing the deltas there to show you how when it was expected to expire and when it actually did, and so on and so forth. And here's the output. And you'll see that it was, remember, this is all in nanoseconds. So when the timer was expected to go off and when the timer actually did, it was 853 nanoseconds late. The time it took from the time it actually woke, that the event actually, or the timer executed to the timer when it actually woke up is the next difference, which is 376 nanoseconds. Then when we scheduled from the time it woke up to when it actually got scheduled onto the CPU, that, if you look at, that's the big number right there. That looks like the problem. It's 118 microseconds, which is greater than the 100 microsecond threshold that we wanted to give. So this is where the problem likely lies. So let's analyze a little bit more. This is just a small example of what we could do. And now we're going to look at locking. We're going to use function tracing to trace all locks and the parent functions as well to see where they're called from. And we need to trace both the lock and the unlock functions because we want to know how long locks are held for inside the kernel. And this is what it looks like. So I'm going to do the trace command start again, but this time I'm going to add -p function, which is say, okay, enable the function tracer. Now this could trace all functions within the kernel. We don't want to do that. We only want to trace locking. So the -l means limit the function tracing on what to trace. And it could take wildcards. So we're going to take spin lock, spin unlock, spin try locks, write locks, write locks, and see where these are the things that could cause latency in our system due to locking and locking contention. Now I recorded that, and now I'm going to, if you notice that this function now I'm calling is trace-cmd iterate events. It's not trace-cmd iterate events reverse, because I'm not going backwards this time. I stopped at where I started the timestamp. So, when the timer went off. So when Cyclic test called nanosleep and it registered the timer, that's basically where the cursor is on that last event, because that last one before was the find timer start, was when the timer was first initialized. Now we're going to go forward and just look at all the locks that were held and released and see how long they were held for, and see if that could have been a problem for us. So we're going forward now. And here, remember that we recorded in our data type the timestamps of each of these events. So we had the timestamp of when the timer was initialized, the timestamp when the timer went off, the timestamp that when it was woken up, and the time that the task was actually scheduled in. And now we actually set a state where this lock was held or taken or released. So as we're finding these locks, we're going to record which state they were in when they were taken and released. Now, because we have that information, we're going to have a bunch of linked lists of each of these states. So we know here's the locks that were taken in the start, from the timer was started, from the timer expired, and we have the list of timers when it was woken up, and also when it was scheduled in. So we know now where the locks happened. And we're going to run this code to do end timer and start timer. This kind of does a little bit more work. Again, I'm not going to get into the details of what these functions do. It's a little bit more of a sorting thing, and it calculates how long these locks were held. Again, the source code is available. And also what we're going to look at is we need to know what type of lock they were and how to match it. So we got to look at the function name and make sure that the spin locks are matched by spin locks, raw locks are matched by raw locks, unlocks, whatever. And this determines which way. Is it a start lock? Is it end lock? And then we go, and then we're going to finally do this print lock list, which will go through each of the states. So we call this function for the locks that were taken at the start, after it was expired, after it woken up, and when it was scheduled in. And now this is the function that shows you how we print that out. Simple function. It just iterates through all the locks for each state and prints out the information that we want, like how long it was held for, maybe a number of times it was held. And now when we dump out the data, this is what we get. Again, we see all the information about the wake up, how long it woke up, how long from the time that the interrupt was supposed to go off and when it actually did, the time from when it woke up to the time the interrupt went off, the wake up to scheduling, as well as from the scheduler to where the trace marker went off. But now we have a little bit more information. We have information on how to do or where these locks were taken. So you'll see these are like functions that are being called. So we actually recorded the function that the lock was taken at with the offset. So we have a little bit more information. So we could use this, looking at the debug information of our Linux kernel debug VM Linux, we could actually find the exact spot in the kernel where the lock was taken, which would show you the lock that's held. And we tell you how long each of these locks are held in these locations. And the biggest time we see is, again, at the wake up. So from the time the interrupt went off and it woken up to the time it actually got scheduled, there was something that happened in that time frame that we want to look at. So we go down and look at all the locks, and here's the place where you'll see locks taken from wake up to sched. We'll notice that this lock that was taken in the function sch direct xmit was held for 168 microseconds, which is beyond our 100 microseconds that we care about. So again, now why is this is probably larger than the time that actually caused it delayed? That's probably because the time lock was taken earlier before the time interrupt went off, because this interrupt might have been enabled. But when a spin lock is held, even though interrupts are enabled, you can't preempt. It has to finish until release the lock before something could schedule in. So even though it could have went off at 168, but the timer went off later, and then it still was a long data. So there. Anyway, here's the code that, here's my website and where you can find the code for my files. So trace-cmd.org is where you download trace-cmd and more. And here's the trace-cycle.c, which contains the code that I just presented here. And if you need more questions, feel free to contact me.